Cool. Thank you for the kind introductions and thanks for inviting me. Today, I'm very happy to be here to share our recent efforts on the 3D reconstruction, modeling, and sensor simulation. These works are made with many of my courses from the WABI and the U of T, and I would like to thanks a lot to them and also to the WABI team for the support. The title for my today's talk is Learning in the Wild Sensor Simulation for Autonomous Driving. As you can see from this title, I will mainly focus on the in the wild setting. So the observations are usually often sparse, incomplete, or noises, which are the usual case we encounter in the real world. For example, in the realm of autonomous driving. And here is the agenda today. I will first briefly introduce why we need sensor simulation for autonomous driving and overview and the preliminaries about the sensor simulation systems. Then I will talk about how to reconstruct a virtual environment from the real world data. After that, I will talk about our data-driven approach for sensor simulation. I will talk about the contributions of our sensor simulators, how to make it run efficiently, and how it can enhance the autonomy model. After that, I will talk about our framework to measure the sensor simulation realism from the perspective of autonomy model. This can provide us some guidance to improve or design the simulator. And finally, I will leave a time for discussion and also the questions. So here is the simple figure to overview the autonomous driving system pipelines. Usually it involves several stages. The first stage, we need to collect sensor data like the camera image or a LiDAR point cloud. Then the data is sent to the autonomy stack, including a perception, prediction, and motion planning modules to generate the control signals to drive autonomous vehicles. However, in these pipelines, there are several challenges. For examples, for the self-driving vehicle evaluation, it is very difficult to evaluate self-driving vehicles on dangerous scenarios beyond what can be safely collected. For example, if we want to test what the self-driving vehicle will behave if there is a dangerous vehicle driving in a wrong direction towards us, we're unable to do this in the real world because it's too dangerous. Also, before we deploy the self-driving vehicles on the public roads, we need to test all the scenarios it might encounter in the real world or in operational domain. However, this is very expensive with on-the-road tests because we need to evaluate all the scenarios it might encounter. For the self-driving vehicle training, simulation also provides a lot of benefits. The first benefit is that it can make the training more scalable and efficient. Collecting and annotate data is very expensive, especially for the 3D data in the autonomous driving domains. And the simulation plays out ways to train the autonomy model more efficiently because we can generate infinite pair of data and labels. And more importantly, if we want to train the autonomy model in an end-to-end manner, the self-driving vehicle's decision will affect the subsequent observations and the data it will observe. Then it in turn will affect its decision-making for the next time step. So in order to run the autonomy in an interactive manner, we need to requires the access to modify the sensor data. However, this is infeasible if we train the models on pre-recorded data because we cannot modify the data. So this also causes the need of reactive environments or digital twins to train or to evaluate autonomy models more realistically. And all of the above-mentioned limitations can be alleviated by using sensor simulations. Here is a pipeline with the sensor simulators. So basically, we will need to have a simulator that can generate sensor observations based on the world states of the environment and also the state of the vehicle. Then after we generate the data, the autonomy stack will make the planning signals and also generate control signals. This will update the vehicle state and also the world states. After that, we generate the simulation at the next time step, and we can continue this process to run the system in an end-to-end closed manner. This approach makes the self-driving development more controllable, reactive, cost-effective, and more importantly, it's a much safer approach compared to the on-the-road test. Next, we look at what are the capability of a sensor simulator should be like. A first sensor simulator should be able to allow the users to manipulate the virtual environment. For examples, should be able to move existing actors, to remove all the actors and insert new set of actors, to create new scenarios, or to edit the shadows or the lighting of the environments. It should be also known as to manipulate the static elements, such as inserting or moving the traffic cones or construction items in the scenes. It also should known as to manipulate the self-driving vehicle's behavior. For example, perform a lane change or change the sensor configurations, such as densify or sparsify the LiDAR sensors, to change the field of view, the focal length of the cameras, or to elevating the sensors to mimic the perspective change from a sedan to a truck. All these capabilities allow closed-loop simulations, which allows us to develop the full autonomy stack in immersive and reactive manners. In these videos, we show the human drive scenarios in the top. And if we want to understand how the autonomy will behave if this white sedans change its name from leftmost to the middle lanes, we can then run the autonomy model in this simulation environments. And as you can see, the autonomy model under the test will slow down and gradually turn into the right lane. So this provides a way for us to evaluate the entire autonomy stack end to end. Next, we look at the typical sensor simulation pipeline. It usually involves several steps. In the first step, we need to create digital twins, usually consist of movable objects in the scene and the static background. Then we give the simulation specifications, such as the sensor configurations and the scenarios. It is noted that in this talk, we assume those scenarios are given, and how to generate those scenarios are out of scope. And after that, we run the renderings to generate the sensor data, such as camera and LiDAR. We can also measure the simulated data as realism. This provides some useful gradient for us to improve the simulation results and better design the simulator. Now we first look at how to create digital twins from the wild data. The primary approach used in the industry is to use CAD models designed by artists. Those assets usually allow the users to have a higher controllability over the assets and the environments, and they are usually with good quality. However, it's very time-consuming and expensive if we want to build the digital twins of our city-scale environments, because we need to build all the buildings, all the actors in the scenes. This is very expensive. So it can only be run on smaller scale or limited scenarios. However, in our approach, we directly build the digital twins from the real-world data. This approach is more scalable, diverse, affordable, and since we leverage the real-world data, the simulated data will have a smaller domain gap when compared to the real-world data. Next, we'll talk about the approach to reconstruct the virtual environments from the real-world data. Traditionally, this is usually achieved by running structural motions. However, those approach not work very well for large outdoor driving scenes, because the data collection vehicles are usually running along a constrained trajectories and it's single pass. So it does not have enough viewpoint coverage to reconstruct a dense mesh representation for the scene. Another approach is to leverage more advanced depth sensors such as LiDAR, but still have the similar challenges. For example, the LiDAR points are usually very sparse at distant regions, and they are distributed unevenly. So at higher regions, like the top of the trees, the LiDAR will be very sparse. This will make the aggregated point cloud to be very sparse and have challenges if we want to convert it into a dense watertight mesh representations for the simulation purpose. Now we talk about our approach towards this goal. I will first talk about our work in the iCross for reconstructing assets in the wild data. As you can see from these figures, the input to our system is a sequence of camera videos and LiDAR sweeps. Then we can reconstruct relatable assets, and we can also insert these assets into a virtual environment to create new scenarios and generate the sensor simulation. We'll now describe how it works. To render the asset, we first sample the points along the camera or LiDAR array, and then we query each sample point's scene distance value with a neural network. We can also compute normal by taking the gradient of the scene distance value. Then we can infer the specular and the diffuse property of the models. Then we use a physics-based reflectance model to compute the uniformly scattered diffuse kernel and the view-dependent specular kernel. And we finally composite the diffuse kernel and the specular kernel to obtain the final image rendering. We can also render LiDARs and the segmentation mask from the geometries with volume render, and we simulate the LiDAR intensities using the named surface material. And since our data usually captures from one side of vehicles, so the other side is invisible. To recover those invisible sides, we leverage the structure priors, such as the symmetries of vehicles, to complete those missing regions. Our method also works for non-rigid objects, such as a motorcycle or a wooden scaffolds, construction items blended with the background. With our decomposed limitations, we can also change the lightings and create relighting results. Another approach we tried is to leverage the shape priors from template models, such as CAD assets. Since those assets provides more fine-grained details and part information, such as the wheels, the mirrors, this allows us to identify those regions and can have a fine-grained control over the actors. And specifically, we decompose our vehicle model into vehicle body mesh and rotatable wheel model. These wheels can be shifted, can be scaled, and can be rotated. This is a controllable representations that constrain the degree of freedom during the optimizations and allows for meaningful and realistic manipulation of the actor. And in our approach, we optimize the structured geometric limitations of our asset model, along with the decomposed appearance properties and the lightings. Then we want to minimize some energy term to ensure that the generated assets can match with the real-world data. Our energy term consists of a LiDAR term that encourage the rendered LiDARs can match the real LiDAR. And also, we leverage differentiable render to ensure that the simulated image can match the real image. We also regularize the shape of our optimized model to be smooth and have minimal distortion. And now we show the reconstructed geometries overlaid in the scenes cornered by normals. We can see that the geometries can match with the real objects presented in the videos. Apart from the rigid objects like vehicle, motorcycle, or truck, it is also very important to reconstruct deformable assets such as pedestrians and animals. In our work, we have tried to leverage structure priors such as the skinning model to recover the human from the LiDAR data. We can then put those reconstructed animatable humans into a virtual world and generate LiDAR simulations. And in our work, we show that this kind of data augmentations can improve autonomy models for the pedestrian detections. In order to handle the pedestrians with very complex topology, such as those with heavy clothes or accessories, we leverage more powerful neural field representations to then implicit shape, skeleton, and the skinning representations for the animatable objects. After that, we can extract the animation-ready model from the named neural field representations. And due to the time issues, I will skip this part and go to the sensor simulation part. We will first look at how to simulate sensory data from the virtual environments. We simulate the sensor data, we need to specify the sensor configuration, such as the intrinsics, the extrinsics. We are interested in two types of sensors, most commonly used in the self-driving vehicle. One is the LiDAR sensor, the other is the camera sensor. The LiDAR sensor can provide accurate depth informations, and those measurements are usually robust to different lightings. However, it is more sparse compared to the camera measurements, especially for the distant regions. And the operational speed for the LiDAR is usually slow compared to the camera. In the contrary, camera provides more dense informations, but the depth is not directly available to use, and the capture's colors can be sensitive to the lightings. For example, image taker lifetime might not be very useful for the autonomy to make a good decision. And the primary simulator used in the industry is a game engine based. It requires us to first manually create assets, run physics engine to composite those assets to create a virtual environment, and then run graphics pipeline to render the simulation. This approach is simple and fast to run, but it's, as we mentioned before, it's expensive to create those assets, and also might have unrealistic simulations because it didn't model all the physics that might encounter in the real world. And also, the model trained on this kind of data can have a large domain gap compared to the model deployed to the real system. So it requires some kind of domain adaptation efforts. In contrast to simulate sensors from the game engines, recently there is a trend in the industry and also in academia to simulate sensors from the digital twins reconstructed from the real world. For the LiDAR simulation, representative work is LiDAR sim. In this approach, it first built the digital twins by aggregating all the LiDARs across time. And then during the simulation time, it runs physics recastings to render the LiDAR points. In order to handle the more complex physics and make the simulation more realistic, it also combines the machine learning models to learn the probability for the LiDAR rays to drop or end returns. And after we learn this probability, we can sample from it and drop the corresponding LiDAR rays. For camera simulations, there are different approaches in the literature. One is a view warping-based approach, usually involves first build a proxy geometry to provide depth informations, and then it can use this geometric information to warp the information from a source image to a target frame. And after that, we can fuse those information to generate the simulated results. Another approach is a mesh rendering or inverse rendering based approach. Those usually involve first create a texture mesh orientations and then use rasterization based renderings to combine with machine learning to generate the final results. This approach is fast to run and unknowns easy manipulation because how to manipulate a mesh is well studied in the graphics literature, but it heavily relies on the quality of the reconstruction mesh. And unfortunately, it's usually very challenging to reconstruct a good mesh orientations for the large outdoor scenes. Another
Before we ask a quick question.
Yeah.
Okay, pause here. I think actually, Florian, you've got your hand up if you've got your question.
Yeah, sorry, thanks. It's like on the previous section of the talk for the digital twinning of the street scenes, especially this one here. So what is this is like the SDF based like estimation. This gives you like a volumetric thing, not a mesh, right?
Yeah, so in this work, we use mesh orientations. So in the previous work, we use the volumetric rendering-based approach. Are you referring to this work or?
Yeah, to this work.
Yeah.
So this is, sorry, is this volumetric or a mesh?
Volumetric, yeah. Within the SDF orientation from it, but we can extract a mesh from the SDF field.
Gotcha. And what is the data that goes into this? So you have multiple camera frames and multiple LiDAR frames that are all used for one single car?
Yeah. We so the vehicle is the data collection vehicle is driving on the street and collect a sequence of camera image and also a LiDAR sweeps. So given those data, we want to reconstruct a 3D rotations. Yeah, that can be efficiently rendered and simulates new variations to create new scenarios. Yeah, that's the
Okay.
purpose for it.
And sorry, and related question, how do you in order for this to work, you need to mask the object from the background, right? So you assume that you have a priori knowledge of a mask of the object.
Yeah, there are two approaches to decouple the foreground and background. One is, as you said, we can use off-the-shelf segmentation models to mask out the foreground from background. And we can also leverage two radiance models, one to model the foreground and the others to model the background. And because of the multi-view geometric constraints, it can lens to also separate the foreground and background.
Okay. Okay, that makes sense. Oh, and okay, sorry, last question. How many, like for any given car, like how many frames do you usually have? Like
Yeah,
of camera and lidar?
yeah, because those cars are usually taken by the side camera, so maybe like 20 frames.
Okay.
Yeah,
Okay, cool. Thanks.
yeah. Thank you. Thanks for question. Yeah, let's continue on
I always have another quick one.
Yeah.
So a lot of these are reconstructing geometry
Mhm.
from these, but technically a lot of these are dynamic objects.
Mhm.
So there's kind of two levels to my question. Like when we're reconstructing a lot of the components from this, does that also at least take into account like the wheels on the car? Do they construct the mesh such that they also turn and correspond with gripping the ground?
Yeah. So if we use a neural field type of representations, it's very difficult to recover these wheels because they are very small and the observation of those are very limited. So to reconstruct those fine-grained parts, we leverage the prior information from some CAD models. So we have a body mesh and also wheel models that can be optimized. In this way, we can learn the wheels.
Okay. But I was also thinking about like the more forward thinking
Yeah.
part of this question too. And it comes into play more for like the examples when you're making the digital twins for people.
Mhm.
So like understanding the behavior of a person is a lot more than the geometry or replaying them.
Mhm.
So maybe I was wondering, simpler version of this question, or for part one is, do you like replay the people and like the particular motion that was recorded for them inside of the simulation? Or is there also plans to like learn a behavioral model on top of that mesh and be able to like reuse and repopulate people that were like maybe recorded in one city to the next city?
Yeah. So this is a good question. I think so for the animation of this mesh, there are some models that if we given a trajectories, it can generate the motion or the 3D pose sequence for the humans. So all the thing we require is the trajectories of the humans. Yeah. There are some model to generate the trajectories of human given the map informations, but yeah, I think that's beyond the scope of this talk. Yeah, how to generate the trajectories for the humans. Yeah.
Okay, thank you.
Thank you. Yeah, and I think we can continue from here. So another line of approach we want to focus is a neural rendering based approach. In those approach, it usually learns a composition of neural radiance representations and then leverage volume rendering to generate the scene simulations. Those approaches usually can generate very realistic renderings and enables some level of controllability over the scenes, but is usually slow to run because it's based on the nerve, which is slow to renders and is not as fast as the rasterization-based rendering methods. In our latest work, Unison force handle this type of approach. We can now talk about how it works. So we first generate a compositional scene representation parameterized with multi-resolutional neural feature grids. This representation is controllable and can create new scenarios if we update the pose of each actor in the scene. Then we can cast arrays based on the sensor configurations. And we leverage the structure of a 3D scene to efficiently sample the parry points on each ray. Our motivation is that the outdoor scenes are usually dominated by free space. So we can skip the sample points that are far away from the scene surface. we use the aggregated LiDAR to provide the priors on these samplings. So specifically, we create occupied mask by aggregating all the LiDARs, and then during the samplings, we'll only keep those samples that fall inside occupied voxels in aggregated LiDAR mask. In that way, only the samples close to the scene surface will be kept. And this can significantly reduce the number of samples for renderings and can speed up the rendering speeds. After that, we trilinearly interpolate the feature grid and combine with the redirection to generate a view-dependent feature descriptor. This is then alpha composited based on the estimated geometries to generate a parade feature, and also a parade depth for the LiDAR rendering. So far, we have talked about how to render ray features given a camera pixels or LiDAR laser beam. And recall that our goal is to leverage the Unisim to build a controllable digital twins for closed-loop simulation. This means the autonomous system might deviate significantly from the original trajectories in the log in order to respond to new scenarios. So we make several enhancements to our model to better handle this kind of extrapolation and generates the simulation at the new scenarios more realistically. First, for the camera simulation, we combine the volume rendering with image-based rendering to perform a hybrid neural rendering. Specifically, instead of directly render the RGB color, we volume render a feature map, and then we send this feature map to our CNN network to output the final image. This CNN network can then to reduce the artifacts in the rendered image and can then to hallucinate the invisible parts of the objects or the scenes using adversarial trainings. For LiDAR renderings, we leverage another MLP network that takes the volume rendered ray feature to generate a view-dependent intensity for the LiDAR. In addition to the hybrid neural volume rendering, we also then data-driven shape priors for the dynamic actors in the scenes. Specifically, for each actors in the scene, we initialize a latent code for it, and then we use a Hyper network to map this latent code to predict a dense feature grid for each actor. So this Hyper network is then across different actors, and it can learn some shared priors across the same class of actors. This allows us to better handle the objects that are presented in the distant regions, because for those distant actors, we only have very sparse observations, maybe only several LiDAR points, and it's very difficult to reconstruct the full geometry for those distant actors. So we leverage priors that land in the nearby regions to help the completion of those distant actors. With these two enhancements, we can simulate LiDAR and a camera with Unisim in a more realistic and controllable way, and enables more fine-grained controllabilities and closed-loop simulation. Now we show that the Unisim reconstruction results. This video shows the reconstructed depths, the normals, and also the rendered image. And we can also generate high-quality LiDAR rendering compared to retracing-based baseline methods. LiDAR sim, Unisim can generate more smooth LiDAR, as you can see from the LiDAR rings, because it has a more expressive scene rotation. And now we look at the controllability of the simulators. We first show that we can remove existing actors from the scenes. And we can also run this at scales. It also works for the different time in a day, like the daytime, the nighttime, and also different weather conditions, like the cloudy day or with very strong sunlight. We can also insert new actors to the scenes, like this gray sedans, which is reconstructed from the other scene. We can also remove all the actors in the scene and insert multiple new actors to create new scenarios. We can also manipulate actors, such as changing the road from turning left to going straight for this white sedan. We can also swap actors, such as the gray sedan and the white sedan. And we can also manipulate the self-driving vehicles viewpoints shift to left, to the right, and elevating the sensors and lowering the sensors. And here is more results running at scale for different kind of scenes in the urban driving scenarios. We can also estimate outdoor illumination as a high dynamic range sky dome, such as the sun directions and the sky environment map. This results in a reliable digital twins and the environmental lighting map. Using these reliable digital twins, we can modify them and generate augmented scene rotations. And then we perform the physics-based rendering to generate some lighting relevant data, such as the normal map, the depth map, and also the shadow map. With this lighting relevant buffers and estimated source light and target light, we can then perform neural deferred rendering to render the camera videos of the simulated scenes under different lighting variation. And in this example, we show the renderings and the 3 different lighting map. We now show that the rendering results of the same scenes under a new lighting conditions. Notice that the new sun positions and the sky appearance result in modified appearance and the shadows in the right videos. We can also do this at scale, generating new temporary consistent and 3D aware lighting variations of the same scene from a whole library of estimates and actual HDR sky domes. So you can see we can change lighting to a dark time, to the more sunlighting environments. We can also manipulate the sun directions, result in the editing of the shadows. In this example, we rotate the sun directions, and you can see the shadows will change and rotate. We can also do this at scale on a wide variety of scenes. As you can see, the shadows of the actors and the background will be casted to the ground in a temporary consistent manner and realistically. In addition to modified lightings, we can also perform realistic actor insertions of uncommon objects such as construction items, the traffic cones, and insert them in a lighting-aware manner. And next, we talk about how to make the simulation more efficiently. In the Unison papers, we leverage the structure of 3D scene to efficiently sample the query points on each ray. This results in reduced computations, but it's still not real-time because of the underlying limitation of the ray tracing-based rendering techniques. This can limit the applications that requires real-time simulation, such as closed-loop trainings or vehicle in the loop. In our ICCV paper, we propose a new rasterization approach to speed up the Unison trainings and rendering, can make a rendering in real time. Specifically, we take the reconstructed mesh from the Unison and also unfold the mesh to obtain a UV mapping and create a learnable UV feature map. For the distant regions like the sky or distant buildings, we model them with multiple neural skybox. In this way, we can render the 4 scenes. Similarly, we also create UV feature map for each of the neural skybox. Then we can rasterize those limitations to generate multiple feature buffers. We can then run neural deferred shaders on those buffers to create a set of rendering layers for the scenes and also for the skies, the backgrounds. And finally, we can composite those layers to generate the final image. In this way, we can speed up the rendering speed to over 100 FPS for the full resolution image. And this video shows the interactive rendering of the driving scenes as well as the drone scenes. Next, we show that our simulations can enhance the autonomy, such as for evaluation and training of autonomous models, as well as closed-loop simulation. We first show that Unison for the autonomy evaluation. This figure shows the perception models results on the replayed mode and also on lane shift new scenarios. Compared to the other simulators, Unisim can generate more realistic simulations when we have a large extrapolations, and this leads to better 3D detections for the autonomy model. And now we show the quantitative results of real to sim and the sim to real for autonomy detections. Compared to the other baselines, our approach can achieve a lower domain gap compared to the other baselines. And this is especially obvious for the more challenged lane shift setting. Since simulation not only affect perception, but it will also affect the other downstream tasks such as the motion forecasting and motion planning. So we report the domain gap metrics by training autonomy models on real-world data and then evaluate these models on the simulated data and compare the detection results, the prediction results, and motion planning results to the models that evaluate on the real-world data. And you can see that our result can achieve lower domain gap compared to the other baselines for the full autonomy stack. The simulated data can also boost the performance when we use them as data augmentations for training autonomous models. We create the augmented simulated data sets to include the replay image and the replay lidars, and also the lane shift scenarios that shift to 0.5 meters and 2 meters to left and right. It's interesting to observe that even using the simulated data alone to train the perception model, we can achieve even better results compared to train the model on all the real data. And we only increase the rendered viewpoints. We do not increase the new scenarios and do not alter the contents. This means that we can improve the data efficiencies of existing data sets to improve autonomy model training. And if we combine the real data with the simulated data, we can further improve the performance. And now we show that Unisim can also be used for closed-loop simulations, which is more similar to how human will drive in the real world. So given a new safety critical scenario, such as an oncoming vehicle, we can create a world state, specify the location of the actor and the self-driving vehicle. We can then render the sensor simulation with Unisim, and then the sensor data is passed to the autonomy model, which will output the bounding box of the detected actors and the trajectories forecasted for each actors. Then it can plan the motion for the self-driving vehicles to drive. We can then unroll the planned trajectories by one time step and update the location of the other actors. This generates a new world state with updated location of the self-driving vehicle and actors. Then we can subsequently generate the new sensor data and then rerun the autonomy at a new time step. And in this way, the autonomy and the virtual environments are actively interacting with each other to create some completely new scenarios than what was observed in the original data set. And next, we will talk about how to measure the simulation's realism or fidelity. We measure the simulation fidelity from the perspective of autonomy model under the test. So a long domain gap means that the autonomy system should behave exactly the same way in the simulator as it would in the real world for the same scenarios, such as having the same motion planning for each time step for the self-driving vehicle. In our SDV work, we study 3 different autonomy metrics. For detections, we use detection agreement to measure the average precision when treating the detection on the real data as ground truth and the detection on the simulated data as predictions. And for the actor future predictions, we consider the average prediction displacement error between the motion forecasting results on the simulated data and the real data. And for the motion planning, we consider the average final displacement error between the motion planning results on the simulated data and the real data. And this figure shows the domain gap evaluation pipeline. We first build the digital twins, simulations, then we can simulate the sensor data and then run autonomy on both the simulated data and the real data. Then we can compare the difference in the autonomy output to measure the domain gap. This metric provides some guidance for us to improve our simulator. We can incorporate the Oracle enhancements from the real data to study which simulation enhancements can reduce the domain gap. That provides some information for us to develop our simulators to model those Oracle enhancements. Here we show some of the Oracle enhancements. In the left, we show the initial simulation of LiDAR. In the middle is the simulated LiDAR with Oracle enhancement, and the right is the real LiDAR. When we compute the original simulated LiDAR and the real LiDAR, we can observe there are some unwritten LiDARs points highlighted in the orange color are presented in the simulated LiDAR, but not exist in the real LiDAR. Based on this, we can then modify the simulated LiDAR to model this LiDAR redrop effect to generate the Oracle enhancement LiDAR and test its importance from the perspective of domain gap. If this metric tells us that this effect is important for the domain gap, that means we should spend some efforts to learn how to model those return rates. Another simulation effect is the multi-return that result in some ghosting points, such as those returned behind the track, highlighted in the orange color in the real LiDAR. The sensor scanning effect will also affect the domain gap. For example, the rolling shutter effects. During the sensors capture data, the sensors usually accumulate these measurements over the time. So if the sensor is in motion during this period, the data can become distorted because the change in the sensor pose throughout the scan. And modeling this effect can improve the render result and also affect the simulation's realism, as shown in recent papers. And this also holds for the LiDAR simulations. We can say that if we do not model the rolling shutter effects, the simulated LiDAR and the real LiDAR rings does not exactly match, but if we simulate with rolling shutters, they will have better alignments. Another sensor scanning effect is a motion blur. So during the simulations, if the actors in the scene is in motions during the scan of a frame, such as for an image or for a LiDAR sweep, the actors' recorded data will become distorted. This is especially common on the highways where actors is moving in a very fast speed. And modeling this motion blur effect can also improve the simulation realism. And in this example, we show that the rendering results, if we do not learn the model with motion blur, we can see that the learned geometry is very distorted and also it's blurry when we look at the appearance and the render image. And if we learn the model with motion blur, we can learn the actors more realistically and render more sharp results. And this also holds for the LiDAR. We can see the moving actors on the real LiDAR and the simulated LiDARs were much better if we model the motion blur effects. Yeah, finally, let's brainstorm the future directions and some related works, and also for questions. So one very interesting direction is to use the sensor simulations for training and validating autonomy. In the Unison paper, we show that the simulator can be used to perform closed loop evaluations, but we didn't show that it can help the closed loop trainings. So if we have an end-to-end autonomy model and end-to-end simulation models, we can then just place this autonomy model in the simulators and let it to explore the environment and then how to drive. This is more similar to how human learns drives. We can learn from the mistake we make. There are some works focused on the closed loop trainings, but as you can see in these figures, they usually focus on toy examples or box level autonomy plannings. So it's not the real case presenting in the real world. In the real world, the input should be sensor data instead of the bounding box of the actors. Some other very interesting application and directions coming up recently are shown in these slides. One is the unsupervised world model learnings. So there are two works. One is for the LiDAR, and the other is for the cameras. So if we can learn the world models, the autonomous agents should be able to understand the 3D worlds and should be able to predict the futures. But most of those world models are based on diffusion models, and it's operated on the 2Ds or videos. So there's no 3D structures incorporated into those models. And if we can incorporate the structures of the 3Ds into those models, we can learn those models more efficiently and also can generate more temporally consistent simulations and the predictions for the futures. Another very interesting application is the climate modelings. If we can model those different weather conditions, such as the snowing days, the raining days, we are able to simulate different weather variations, and this can be also very beneficial for the air force science. Another very interesting paper is coming recently is the human unsupervised scene decompositions. Most of the existing simulators requires the 3D bounding box to separate the dynamic actors and the static backgrounds. This requires human efforts to annotate the neighbors or to use some offline labeling system to generate the actor neighbors. However, in this paper, they show that the dynamic actors and the background can be done in an unsupervised manner through the volume renderings. So if we have such kind of models, we can make the simulation more scalable, and those decomposed foreground and background can also be beneficial for the other computer visions and robotic tasks. And this is the end of my talk. Thank you again for inviting, and thank you again for listening, attending. Yeah. And yeah, any questions?
Thank you, Z. Great talk. Yeah, any question?
Just a comment. Your presentation is like a whole workshop at CDPR. But it's just like you and the team. It's amazing.
Yeah, it's a lot of materials. Yeah, it's from the workshop. Yeah.
I'm just blown away that you guys can be so productive and produce so much good work. It makes me happy because it's a Canadian company, and you guys are rocking it. Everything here is just really cool. Really, really cool.
Yeah, thank you. Thanks a lot. And yeah, a lot of effort is from our whole team. So yeah, very appreciates for our teamwork. Yeah.
So I have a question. Like, so how does it work? Are you full time at Wabi or half time? How do you do that?
Yeah, I'm full time at Wabi, and also PhD at U of T. Is like a joint program. Yeah.
And how long have you been there now? How long have you been at Wabi?
Sorry, can you repeat?
How long have you been doing your Wabi PhD thing?
Yeah, it's more like negotiation between the advisors and the universities. Yeah.
You've been a student for how long?
Yeah, I'm in my fourth years towards my PhD degree.
Maybe. Okay, go ahead.
Oh yeah, I just have a question about the Unisim work. So since you're using the neural radiance fields to generate the scene, what happens when you say take a maneuver that deviates a lot from the maneuver that was taken in the real world? Do you need a generative model to sort of generate what the scene would be if you deviate pretty far from the trajectory in the real world?
Yeah, we have two enhancements specifically designed to handle these large extrapolations. So the first is we use some cell network and adversarial trainings. I can find the slides. Yeah, we have a cell network to take the volume render features and predict the final image. So these same features can then in the latent space of the rendered features to reduce artifacts when do extrapolations, and can then to implement the invisible regions with some kind of hybrids of photometric loss trainings and adversarial trainings. So this is one enhancement. The other is we use a hypernetwork to generate the representations from latent code. So this network is then across multiple actors, so it can learn some shape priors. This is some kind of generalizable models. So it is also able to help to implement the invisible regions for the dynamic actors. So with these two enhancements, we're able to generate more realistic simulations when the trajectories deviate from original recordings. But if this deviation is very fast, is very large, we're still unable to handle this kind of situations, and requires further, further improvements.
I see. Thank you.
I had kind of a high level question. So, I mean, I'll echo what Chris said. It's like very, very impressive work, both in breadth and in quality. You've talked a lot about reducing the reality gap, getting the rendering just exactly right, so that all the sensor data is simulated just perfectly. And you talked a little bit, but not as much, about getting the behavior of the actors in the simulation right, and the way that they react to each other in the simulation. So, like, I wonder what's your perspective? Like, how much of the value of the simulator is derived from getting the sensor data like simulated exactly correctly, and how much of the simulation value is really derived from making sure that the agents actually follow the correct distribution of actions, like the way that they actually behave and interact follows the correct distribution, including getting the long tails of the way that the actors would actually act and interact.
Yeah,
right.
I understand your point. Yeah, this is a very good questions, and I would like to answer in two perspectives. So for the autonomy evaluations, so the scenarios of those actors, the trajectories, are usually given by humans because it's for evaluations. We want to test some scenarios we already know. For example, oncoming vehicle drive towards us, or vehicles merge to our lanes. So we already know those kind of scenarios. We can handcraft it and then test our systems. So this is for the evaluations. For the trainings, we want the model to know a diverse of scenarios. So we might want to leverage some kind of intelligent, maybe scenario generation models, but we didn't go into too much in this work, in the Unisim work. So that's very interesting directions to consider in the futures. Yeah.
Do you think that that diffusion models and generative models can be applied in a similar way to generate diverse and representative interactions between agents? So I guess is diffusion models all you need?
Yeah, I think it depends on your applications. Yeah, for the metaverse, for the other domains, safety is not very crucial. I think the diffusion model is perfect. Yeah, even if the generated result is not temporally consistent or have some artifacts, it will not affect too much of the user experience. But for the autonomous driving, safety is very critical. So we want every stage is controllables and is explainables. We want to have some 3D structures in the process so we can control it. But I don't say that the diffusion models can have such kind of fine-grained controls in its current stage. But maybe in the future they can become better. Yeah.
Awesome, thanks.
what do you think about using language for controllability? Because I've seen like these demos coming out of Wave where you can learn the sort of multimodal model and use language to generate scenes.
That's true. That's true. Yeah, controllability is one side. The other is like the representation side. So in the diffusion models, they are mostly operate on the QDs. So there is no 3D structures in the underlying representation. So it's not guaranteed that the output videos is physically feasible. But if we have underlying 3D representations, we are able to ensure that it's physically feasible. Yeah, I think this is another aspect, but yeah, I also want to learn more about the diffusion models. Yeah, it's very impressive directions.
Yeah, that makes sense. Thank you.
Thank you. Thanks for the great questions.
Okay. Well, thanks for the talk, Z. That was a great talk.
Thank you. Thank you for inviting me, and thank you for attending. Thanks for the awesome questions. Yeah.
All right.
Thanks.
See ya. Thanks, everyone.
Thank you. Thanks, everyone.
Take care.